We are often encouraged to give our old clothes a second chance. Perhaps you have gathered up the items you no longer wear, taken them to a thrift store, or dropped them into a donation bin near your home. But from that moment on, where do they actually go? For many of these garments, the journey has only just begun. They are collected, sorted, and compressed into large bales before being transported across multiple countries. Some eventually reappear in stores and markets, while others are cut into pieces, processed, and transformed into entirely new, high-end fashion garments. This film will follow the trail of these discarded clothes to uncover how they enter a global marketplace and take on an entirely new kind of value. Stay with us until the end to discover the true second life of used clothing, a journey that may stretch farther than anyone could ever imagine. Fast fashion is flooding the world, with roughly 100 billion garments produced every year, the equivalent of more than 3,000 new items appearing every second. But behind that dizzying pace lies an endless stream of waste. Every second, a truckload of clothing is either burned or sent to a landfill. Over the course of a year, the world generates around 92 million tons of textile waste, enough to turn landfills into enormous clothing graveyards. American writer Mark Twain once said, "Clothes make the man." But across Africa, the items discarded by the West are creating something far greater: jobs, markets, street fashion, and even waste crises. A shirt left behind in Paris or London may end its journey in Accra, where its fate is decided all over again. The journey begins when clothes that are no longer wanted are dropped into donation bins located outside supermarkets, in parking lots, at schools, churches, and thrift stores. With one simple gesture, each item enters one of the largest textile collection networks in the world. What few people realize is that most of these donation bins are not operated by local governments. Instead, they belong to charities or textile recycling companies. Rather than handing the clothes directly to people in need, many organizations sell everything they collect to sorting companies at a price calculated by the ton. The money raised is then used to support community programs, while the clothing continues into the global commercial supply chain. Once the bins are full, specialized trucks collect their contents along pre-optimized routes, much like a parcel delivery network. Clothing from hundreds of collection points is brought to a central facility, where it is compressed into bales weighing anywhere from 500 to more than 1,000 pounds, before being transported to sorting plants. The scale of this network is far greater than most people realize. The European Union alone discards around 5 million tons of textiles every year, nearly 12 kilograms per person. Handling that enormous volume of clothing requires thousands of donation bins, thrift stores, collection trucks, and storage facilities to operate continuously as part of a vast logistics system. At the sorting center, each bag of clothing is opened, emptied onto a conveyor belt, and inspected mostly by hand. In just a few seconds, workers must assess the material, condition, style, season, brand, and degree of damage of every item. Clothing that remains in good condition is separated into categories such as children's wear, coats, jeans, footwear, or premium-grade items, while pieces that are torn, faded, or missing components are assigned to lower grades. A large facility may create hundreds of product categories, yet most of its revenue often comes from only the top 30% of the highest quality clothing. Meanwhile, around 74% of items that are no longer suitable for reuse or have little resale value can still become raw material for further recycling. Sorting, therefore, is about far more than simply separating clothing by type. It is the stage that determines which items still retain value as wearable garments, which are valuable only for their materials, and how the entire shipment will ultimately be priced. After sorting, items that are nearly new, fashionable, or made by well-known brands are set aside for markets with stronger purchasing power. Before reaching the shelves, they are usually inspected carefully for damaged seams, broken zippers, and stains, then washed, deodorized, steamed, or pressed. Some pieces also receive minor repairs, replacement buttons, and new price tags. As a result, a shirt once dropped into a donation bin can reappear in a charity shop, thrift store, vintage boutique, or on a resale platform in the United States or Europe, looking almost like a new product. The US secondhand apparel market alone grew by around 14% in 2024 and is projected to reach $74 billion by 2029. More ordinary categories, items that are older or difficult to sell in their original markets, are compressed into bales and sold by weight to international traders. India is one of the key destinations in this network. In cities such as Delhi, Mumbai, and Hyderabad, thousands of bales of used clothing are opened each day for merchants to inspect and select. Within just a few hours, a bale weighing hundreds of kilograms can be divided and distributed among dozens of different retailers, ranging from low-cost street markets to specialized secondhand stores selling branded clothing. According to industry estimates, the global secondhand clothing market is currently worth more than $250 billion and is projected to exceed $350 billion before 2029. This growing demand has helped millions of garments remain in use for several additional years, while supporting the livelihoods of hundreds of thousands of small traders, sorters, and supply chain workers in India and many other countries. Not every item that reaches India finds a buyer. Clothing that is badly torn, moldy, or made from blended fabrics that are difficult to recycle is often abandoned around markets and sorting facilities, forming large piles of textile waste. India currently generates around 7.8 million tons of textile waste each year, although most of it comes from domestic sources. Some of this waste is sent to landfills or burned to reduce its volume. Burning clothing that contains synthetic fibers and dyes can release fine particulate matter and a range of toxic gases, degrading air quality and increasing the risk of respiratory illnesses among people living near disposal sites. Meanwhile, textiles buried in landfills can also release microplastics and chemicals into the soil and water, creating an environmental problem that may persist for many years. But not every item is in good enough condition to return to the secondhand market. Worn-out shirts, torn pants, and fabrics that have lost their shape are sent through a mechanical recycling line to recover the fibers that still retain value. First, the clothing is fed into an industrial cutting machine, where continuously rotating blades tear it into small pieces of fabric only a few centimeters across. Reducing the material to a smaller size helps it move more steadily through the system, while creating additional cut edges, allowing the next fiber opening stage to proceed faster and more evenly. By the end of this stage, the original form of the shirts, pants, and dresses has almost completely disappeared, leaving behind a uniform stream of shredded fabric ready to be pulled apart and opened back into loose fibers. After being cut into smaller pieces, the fabric fragments move into a fiber opening machine, where multiple rotating cylinders densely covered with steel teeth continuously pull, comb, and break apart the woven structure. Layer by layer, the fabric is torn open, gradually releasing the tightly interlaced fibers until the material becomes a loose, cotton-like mass. This process usually takes place in several stages, progressing from porous tearing to fine fiber opening. At each stage, the fabric pieces become smaller, while an air extraction system simultaneously removes dust, fiber fragments, and other lightweight impurities. Depending on its configuration, an industrial fiber opening line can process approximately 50 to 3,000 kilograms of material per hour. Systems designed to produce fibers of sufficient quality for spinning typically operate at around 300 to 1,200 kilograms per hour. The mechanical tearing significantly reduces both the length and strength of the recovered fibers. For this reason, they are usually blended with virgin cotton, recycled polyester, or longer man-made cellulosic fibers. In some applications, the blend can still contain up to around 70% recycled cotton and be spun into any 24 to any 30 yarn. Once the material has been opened into a loose mass, the recycled fibers are fed into a drawing machine to form a thick strand known as a sliver. This is not yet weaving yarn, but an intermediate material that gathers thousands of short fibers into a continuous, uniform, and manageable stream. Inside the machine, several slivers are combined and drawn through pairs of rollers operating at progressively higher speeds. This evens out thick and thin sections while aligning the fibers in the same direction. Some modern machines can deliver sliver at speeds of up to around 1200 meters per minute, making precise control of thickness essential. Finally, the sliver is coiled inside large cans to prevent tangling and maintain stable tension. Its uniformity is critical, since any thick, thin, or loosely formed section can become a weak point when the material is spun into finer yarn. Once the material has been opened into a loose mass, the recycled fibers are fed into a drawing machine to form a thick strand known as a sliver. This is not yet weaving yarn, but an intermediate material that gathers thousands of short fibers into a continuous, uniform, and manageable stream. Inside the machine, several slivers are combined and drawn through pairs of rollers operating at progressively higher speeds. This evens out thick and thin sections while aligning the fibers in the same direction. Some modern machines can deliver sliver at speeds of up to around 1200 meters per minute, making precise control of thickness essential. Finally, the sliver is coiled inside large cans to prevent tangling and maintain stable tension. Once the yarn has been spun, it is transferred to weaving machines to produce new fabric. First, thousands of warp yarns are stretched in parallel across the loom under carefully controlled tension. Even a single yarn that is too tight or too loose can create streaks, gaps, or bring the entire production line to a halt. As the loom operates, heddle frames continuously raise and lower groups of warp yarns to create an opening for the weft yarn to pass through. After each insertion, the reed beats the weft firmly into place, locking the yarns together. This cycle repeats thousands of times every minute, gradually forming a continuous fabric sheet that can stretch for hundreds of meters. The way the warp and weft yarns interlace determines the fabric's characteristics. Plain weave creates a stable, balanced surface. Twill weave produces a softer and more durable fabric, while satin weave delivers a smooth, lustrous finish. A 3-second one-twill weave is commonly used to create its signature diagonal texture and improve abrasion resistance. Modern weaving machines can perform around 700 to 1,500 weft insertions per minute, while using sensors to detect broken yarns almost instantly. The finished fabric is then wound into large rolls and inspected for defects such as streaks, knots, pinholes, or uneven density, before moving on to the finishing and garment manufacturing stages. After finishing, the fabric rolls are spread into multiple layers across an automated cutting table. A CAD system calculates the most efficient arrangement of each pattern piece to maximize fabric utilization, reducing waste to around 10 to 15%, far lower than with manual cutting. A CNC cutter then cuts through dozens of fabric layers at once, with millimeter-level precision. Components such as the front and back panels, sleeves, collars, and pant legs are transferred to sewing lines, where they are assembled using different types of seams. A standard t-shirt typically requires around 15 to 25 sewing operations, while a pair of jeans may go through 40 to 60 steps, including joining the main panels, attaching pockets, installing the zipper, fastening buttons, and finishing the hems. Finally, loose threads are trimmed, the garments are pressed, and their dimensions, seam strength, and overall appearance are inspected before they are folded, packaged, and shipped. After a long journey that began with discarded clothing, the recycled fibers have now been transformed into entirely new garments, ready to begin another life cycle. From a small donation bin, used clothing can enter a global network. Garments in good condition are cleaned and resold. Lower-grade items are shipped to distant markets, while damaged pieces are torn back into fibers and transformed into new fabric. But not everything finds a second life. Many garments still end up in mountains of textile waste, placing enormous pressure on the environment and local communities. And that is not the most surprising transformation in recycled fashion. In the next journey, an entirely different type of waste will be turned into fiber, woven into denim, and transformed into stylish new jeans. Keep watching to discover what is really hidden inside that fabric. What you throw away every day could be the very thing you are wearing right now. Plastic bottles, containers, trays, and packaging are often discarded after just a few minutes of use, yet the material itself can remain in the environment for hundreds of years. But at the other end of this waste stream, an entirely different journey is taking place. Inside modern factories, discarded plastic is sorted, cleaned, melted, and spun into recycled polyester fiber. These fibers are then blended with cotton, spun into yarn, dyed with indigo, woven into denim, and finally cut and sewn into a finished pair of jeans. So how can a pile of hard, dirty, mixed plastic waste be transformed into the soft, durable fabric we know so well in everyday life? Join Factron process as we step inside the factory to uncover the complete journey of turning plastic waste into jeans. For more than a century, jeans were woven primarily from cotton, but the arrival of polyester made denim more durable, better at holding its shape, and more flexible. Today, polyester has even become the most widely produced fiber in the world. What may come as a surprise is that most recycled polyester does not come from old clothing. Instead, it begins with used PET bottles, containers, and packaging. An item discarded after only a few minutes can continue to exist for years in the form of a pair of jeans. However, not every type of plastic can be spun into fiber. PET must be precisely separated from the mixed waste stream before nearly all adhesives, colorants, metals, and other polymers are removed. That is why the most impressive part of this process is not simply turning hard plastic into soft fabric. It is identifying the right material among tons of waste and giving it an entirely new life cycle. The journey begins in residential neighborhoods, supermarkets, offices, restaurants, and material recovery facilities where used plastic bottles, containers, trays, and packaging are collected. Some are sorted at the source, but most still arrive at the plant mixed with paper, metal, organic waste, and many other materials. At the receiving area, trucks lift their containers or use tipping mechanisms to unload the entire load onto the storage floor. Within just a few minutes, tons of material form massive piles in every color and shape. Wheel loaders continuously scoop the plastic into a feed hopper. From there, a steel conveyor carries the material toward the bale breaker. The plastic bales, previously compressed to save space during transportation, are torn apart by rotating shafts fitted with steel teeth. Once loosened, the plastic is spread into a thin layer across the conveyor. Workers positioned along both sides quickly remove batteries, electrical wires, bulky objects, organic waste, and anything that could damage the equipment. At this stage, the plant still does not have material ready for fiber production. What lies before them is only a mixed stream of waste containing many entirely different types of polymers. The mixed stream of plastic waste first enters a massive steel screening drum that rotates continuously. Inside, the material is lifted and dropped thousands of times, allowing dust, sand, broken glass, and small fragments to fall through the screen openings, while larger bottles, containers, and packaging continue moving forward. Immediately afterward, a powerful airstream pulls paper, thin plastic bags, and other lightweight materials away from the conveyor. An overhead magnet captures steel, while an eddy current separator generates a contactless repelling force that sends aluminum fragments into a separate chute. But the greatest challenge lies in distinguishing plastics that look almost identical to the human eye. The material is spread into a thin layer and carried beneath near-infrared sensors. Within just a few thousandths of a second, the system identifies the reflected spectral signature of PET, HDPE, PP, and PVC, then precisely activates individual compressed air nozzles to blow each item into the correct collection bin. Suitable PET is retained for polyester fiber production. HDPE and PP are directed to other processing lines, while PVC must be removed with extreme care because even a small amount can contaminate an entire batch when the plastic is heated. Once sorted, the plastic bottles, containers, and trays begin to lose their original shape. A conveyor carries them directly into the hopper of an industrial granulator, where a large rotor fitted with multiple alloy steel blades spins at several hundred revolutions per minute. Inside the cutting chamber, the moving blades continuously pull the material downward, force the plastic against a row of stationary knives, and slice it into smaller pieces. Within seconds, an intact PET bottle is reduced to dozens of irregular fragments. Beneath the rotor, a perforated screen controls the final particle size. Only pieces small enough, typically around 0.4 to 0.8 inches, can pass through. Larger fragments remain inside the chamber and continue circulating across the blades until they reach the required size. The result is a relatively uniform stream of plastic flakes. Immediately after leaving the granulator, the stream of plastic flakes is fed directly into a precision sorting system. A vibrating conveyor spreads millions of flakes into a thin, even layer, allowing each piece to pass through the inspection zone without overlapping. Above the conveyor, high-speed color cameras continuously scan the material stream. The system can identify flakes that are too dark, discolored, heat-damaged, or still contaminated with paper, metal, and other foreign materials. Some production lines also use near-infrared (NIR) sensors to verify the polymer types again, because after being shredded into small pieces, PET, PVC, and other plastics can become almost impossible to distinguish with the naked eye. The moment an out-of-spec flake is detected, the control system calculates its exact position. Within just a few milliseconds, an air jet beneath the conveyor is activated, blowing the defective piece out of the main material stream. Only after passing every one of these inspections are the plastic flakes considered uniform enough to move on to the next stage of the recycling process. Immediately before entering the extruder, the PT flakes spend several hours inside a dehumidifying dryer, where ultra-dry air and a network of sensors remove virtually every trace of moisture. Because for PET, even a tiny amount of water is enough to break the polymer chains during melting and compromise the quality of the entire batch. Once fully dried, the flakes drop into the hopper of the extruder. Inside, a steel screw nearly 10 feet long rotates continuously, pulling the material forward while compressing it through multiple heating zones. The rigid plastic flakes gradually soften before merging into a smooth, homogeneous stream of molten polymer. As the material moves deeper into the barrel, pressure builds to several thousand psi, forcing the melt through ultra-fine metal screens that capture the last remaining contaminants, while a vacuum degassing system continuously removes moisture and volatile compounds. Finally, the purified polymer is forced through a die, emerging as dozens of thin plastic strands. These glowing strands pass through a cooling water bath before entering a high-speed pelletizer. In an instant, the continuous strands are chopped into millions of nearly identical rPET pellets. Small as they are, these uniform pellets become the industry's standard raw material, ready for the next stage, where they will be transformed into brand new polyester fibers. The rPET pellets are treated in a solid-state polymerization system to improve viscosity and strength while removing residual moisture. Metering valves then feed them steadily into the extruder, ready to be spun into thousands of continuous filaments. The rPET pellets are fed back into an extruder, where a rotating steel screw continuously melts, blends, and pushes the polymer forward under precisely controlled heat and pressure. The molten plastic then passes through an ultrafine filter before being pumped toward the spinneret, a metal plate containing hundreds or even thousands of microscopic openings. As the polymer is forced through these holes, it instantly emerges as continuous filaments nearly as fine as human hair. Directly beneath the spinneret, a stream of cool air solidifies the filaments almost immediately. They then pass through a series of rollers, rotating at progressively higher speeds, stretching the fibers to several times their original length, and aligning the polymer chains in the same direction. This makes the filaments thinner, yet significantly stronger. Finally, an extremely thin layer of finishing oil is applied to reduce friction and static electricity. In just a matter of minutes, rigid plastic pellets have been transformed into thousands of continuous polyester filaments, ready to be cut into staple fibers for the textile industry. Thousands of filaments are gathered into a thick tow, crimped, heat-set, and cut into cotton-length staple fibers. After being opened and quality inspected, the recycled polyester fibers are ready to be blended with cotton before moving on to the dyeing process. After being blended with cotton and spun into yarn, the yarn packages enter the stage that creates the iconic color of blue jeans. Hundreds of warp yarns are gathered into a broad sheet or thick ropes and continuously fed through either a rope dyeing or slasher dyeing line. Remarkably, the indigo solution inside the vats does not yet display its familiar blue color. Only when the yarn is lifted from the bath and exposed to oxygen in the air does oxidation begin, gradually revealing the blue shade across its surface. For this reason, the line repeats the dipping and oxidizing cycle between 6 and 12 times. Each pass adds only a very thin layer of color, allowing the shade to build evenly and become more durable. Once the required depth of blue has been reached, the yarn is washed to remove excess dye, dried, and coated with a thin protective sizing layer so it can withstand friction while moving at high speed through the loom. Interestingly, indigo remains concentrated mainly on the outside of the yarn instead of penetrating deeply into its core. Over years of wear, this feature produces denim's distinctive fading patterns. Once dyeing is complete, thousands of blue warp yarns are loaded onto the loom and stretched parallel across a path extending for dozens of yards. Between them, light-colored weft yarns are inserted back and forth at speeds that can reach hundreds of passes per minute. The loom's harness frames continuously raise and lower selected groups of warp yarns, opening narrow sheds for the weft to pass through. While the reed immediately beats each new strand firmly into position. This cycle continues without pause, gradually building the twill weave and the diagonal ribs that give denim its unmistakable appearance. Throughout the process, tension sensors, high-speed cameras, and automated control systems watch for broken yarns, color variations, and surface defects, ensuring that every yard of fabric meets the required standard. At the end of the line, the finished denim is wound into massive rolls, ready to move into cutting and sewing. Material that once existed as discarded plastic bottles has now completed a remarkable transformation, becoming the durable fabric used in billions of pairs of jeans around the world. From rolls of denim that have already been softened and stabilized against shrinkage, the process moves into the cutting area, the point where the material begins to take the shape of a finished garment. Layers of fabric are stacked high and secured beneath a vacuum compression frame to maintain precision. Guided by digital cutting patterns, an automated cutter moves across the spread, while its heat-resistant alloy blade slices through dozens of thick denim layers at once, without shifting or distorting the edges. Every component, the front and back panels, pockets, waistband, and belt loops, is numbered and sorted separately before being transferred to the sewing floor. The sewing area operates with hundreds of specialized machines. Each one performs a specific seam. Double needle machines construct the main leg seams, overlock machines finish pocket edges, and chain stitch machines create decorative details. Alloy steel needles pierce the heavy denim at high speed, while electronic sensors regulate thread tension to keep every stitch uniform. Cotton-wrapped polyester thread is used to improve strength while creating the contrasting stitch color that has become a signature feature of jeans. Workers inspect each garment directly at the sewing station, making sure the stitch lines remain parallel and every rivet is secured at the correct stress point. The completed jean bodies move directly into the hardware setting area, where rows of hydraulic presses operate continuously. Brass buttons, rivets, and zippers are automatically fed through vibrating chutes and pressed securely into high-stress areas such as the pockets and waistband. In the finishing area, machines serve only as supporting tools. The final result still depends on the skill of human hands. Finishing workers use sandpaper, pumice stones, and stiff bristled brushes to abrade selected sections of the fabric, creating the natural fading that would normally appear only after years of wear. Certain details are treated with handheld airspray tools or mild bleaching agents, allowing the denim color to fade gradually according to the intended design. Each pair of jeans is then hung separately beneath inspection lights, so its color and shading can be carefully examined. Afterward, the garment is steam treated to soften the fabric and stabilize its final shape. No two pairs emerge exactly alike. Every abrasion mark and every faded shade carries the individual touch of the worker who created it. As the process enters the finishing area, the noise of the machinery gradually fades. Each pair of jeans is laid flat beneath bright white lights, where the stitching, durability, and faded color are carefully inspected. Garments that meet the required standards are marked, folded to a preset shape, and transferred to the automated packaging line. Here, machines apply labels, print traceability codes, and seal the packages, while technicians monitor each production batch from a central control screen. Finally, the jeans are packed into boxes and recorded in an electronic tracking system, bringing their transformation from discarded material to a finished pair of jeans to a close. And that is how two streams of material once considered worthless are brought back into the production cycle. Old clothes are collected, sorted, and given another chance to be used, while discarded PET bottles are cleaned, shredded, melted, spun into polyester fibers, and blended with cotton to create strong denim fabric. From massive sorting centers to spinning, indigo dyeing, weaving, cutting, sewing, and finishing lines, every stage transforms waste into a new source of raw material. A single pair of recycled jeans cannot solve the entire problem of fashion and plastic waste, but it proves that discarded materials do not necessarily have to end their journey in a landfill. When technology, industrial scale, and consumer choices begin to change together, materials once treated as waste can start an entirely new life. Would you be willing to wear a pair of jeans made from recycled clothing and plastic bottles?